Hello guys, welcome back to my channel, and in this video I would like to do a nice important integral. When I first saw this integral, I felt internally that this integral has to go on my YouTube channel. So it has a form similar to something we've dealt before, but it's totally different. It's deceivingly different. So let's get started and you'll see exactly what it is. Okay, so for our purposes, let's consider I, which is basically defined as integral from 0 to pi over 4 of natural log of sine theta d theta. And you may immediately recognize this if you are an avid viewer. This is similar to an integral we've done before, integral from 0 to pi over 2 of natural log of sine theta d theta. And for calculating this integral, we had used extensive symmetry because of the fact that sine of pi over 2 minus theta is uniquely cosine theta, and then having cosine theta we added both the integrals, so we had 2I is equal to natural log of sine theta plus cosine theta, and uh, sorry, it was natural log of sine theta times cosine theta, yeah, if I'm not wrong. After combining the two integrals, then we used the symmetry of the graph of this function basically, and then we came up with an answer of minus pi over 2 times natural log of 2. So please check that video out if you haven't already. And the problem is we can't use symmetry for calculating this because sine of pi over 4 minus theta is not equal to any unique alternate trigonometric function, so we run into trouble there. But one thing we can do is notice the natural log. We can write sine theta as e to the I theta minus e to the negative I theta divided by 2I using Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. And it's a logical way of going about this because natural log and exponential are basically inverse functions, so there is a chance of some things cancelling out in the future. So we have integral from 0 to pi over 4 of natural log of e to the I theta minus e to the negative I theta over 2I with a d theta. Now let's convert everything into negative powers in the numerator, and you'll see exactly why I'm doing this. So we have 1 over e to the negative I theta minus e to the negative I theta all over 2I with a d theta. Now taking the LCM, integral from 0 to pi over 4 of natural log of 1 minus e to the negative 2I theta over e to the negative I theta times 2I d theta. And now using some properties of logs, say if you have natural log or log to any base, let's say natural log in this case of pq over rs, you can decompose this as natural log of p plus natural log of q minus natural log of r minus natural log of s. So whatever is in the numerator has a plus in front of it, and whatever is in the denominator has a minus in front of it. Using this same property, we can split this into a bunch of integrals. So natural log of no factors in the numerator, so 1 minus e to the negative 2I theta d theta, and all the factors are in the denominator, so all of them will have a negative sign. Integral from 0 to pi over 4 of natural log of e to the negative I theta d theta minus integral from 0 to pi over 4 of natural log of 2 d theta minus integral from 0 to pi over 4 of natural log of I d theta. Let's just write the first integral as it is because it's too much to consider. So let's just simplify all the other things and then we can get to evaluate this. So this using log properties becomes I times theta, and the theta stays inside this integration, minus natural log of 2 times integral from 0 to pi over 4 of d theta minus natural log of I and integral from 0 to pi over 4 of d theta. We have integral from 0 to pi over 4 of natural log of 1 minus e to the negative 2I theta d theta, and this will be theta squared over 2 evaluated from 0 to pi over 4. So I over 2 times theta squared evaluated from 0 to pi over 4. This is natural log of 2 and theta evaluated from 0 to pi over 4 minus natural log of I is I times pi over 2, because I can be expressed as e to the I pi over 2 using this formula. So basically taking natural log on both sides, natural log of I is I times pi over 2. I times pi over 2 and theta evaluated from 0 to pi over 4. So this becomes integral from 0 to pi over 4 of natural log of 1 minus e to the negative 2I theta d theta, plus we have pi squared over 4 squared, which will be I times pi squared over 16 times 2 is 32 minus pi over 4 times natural log of 2 minus I times pi squared over 8. We still can do one final simplification here. So integral from 0 to pi over 4 of natural log of 1 minus e to the negative 2I theta d theta, and this will just be, I think, a negative, because this will be negative 3 pi squared over 24 over negative 4 pi squared over 32. If we take the LCM, we'll make a negative 3 pi squared over 32 along with this I minus pi over 4 times natural log of 2. And now let's actually formally deal with this integral. Notice this natural log is of the form 1 plus x, where x is negative e to the negative 2I theta, and now it's an excellent place to use Taylor series, because our natural log is in the optimal form to use Taylor series, and that was the entire purpose of basically taking negative powers here, so that we obtain the natural log in this form of 1 plus x in the argument. So we can use Taylor series now for this. So sum from k equals 1 to infinity of minus 1 to the k plus 1 over k, which is all inside the integral from 0 to pi over 4 of negative e to the negative 2I theta to the kth power, integral with respect to theta, minus pi over 4 times natural log of 2 minus I times 3 pi squared over 32. Now, assuming uniform and absolute convergence, we can interchange these sum and integral. So we have sum from k equals 1 to infinity of minus 1 to the k plus 1 over k. We can take a minus 1 to the k outside from this initial part. Integral from 0 to pi over 4 of e to the negative 2I k theta d theta minus pi over 4 times natural log of 2 minus I times 3 pi squared over 32. And now minus 1 to the k times minus 1 to the k is minus 1 to the 2k. So minus 1 raised to an even power. 2k will always be even integer. Minus 1 to an even power is 1. So we have those cancelling out, and we have minus 1 to the 1. So minus sum from k equals 1 to infinity of 1 over k times integral from 0 to pi over 4 of e to the negative 2I k theta d theta minus pi over 4 natural log of 2 minus I 3 pi squared by 32. And we can basically use this negative to compensate for the antiderivative of this, the negative that we obtain by the antiderivative of this. So we have sum from k equals 1 to infinity of e to the negative 2i theta k over all the coefficients apart from the theta. So 2ik. So 2ik times k is 2ik squared, evaluated now from 0 to pi over 4 minus pi over 4 times natural log of 2 minus I times 3 pi squared over 32. And this series is much to consider. Let's just call it S and do it on a fresh page. See you there. Okay, so as stated, I've written the series at hand over here with S. Let's go ahead and unplug the upper and lower bound. So we have sum. Basically write the 1 over 2i factor multiplied outside. We have sum from k equals 1 to infinity of e to the minus 2i pi over 4 times k over k squared minus sum from k equals 1 to infinity of e to the minus 2ik0 over k squared. So this is just going to be this part is basically going to be e to the negative I times pi over 2k, but we know that e to the I pi over 2 is nothing but I, so this is I to the negative k power, or you can say 1 over I to a kth power. 1 over I is negative I, entire thing to the kth power, which we can express writing the negative 1 separately as negative 1 to the k times I to the k. So we have 1 over 2i sum from k equals 1 to infinity of minus 1 to the k times I to the k over k squared minus e to a 0 power is 1. So we have sum from k equals 1 to infinity of 1 over k squared. Now the hard part is figuring out what this series is, because this is pretty easy to find out. This is just the Riemann Zeta of 2. But still, this is like the hard part, right? But don't worry, if you just want some perspective, we can write some terms. So just for this part, let's write terms. When k equals 1, we have minus 1 to the 1 minus 1 and a single I. So we have negative I over 1 squared, and then for k equals 2 we have minus 1 squared, so that goes to 1, and I squared, which will be minus 1, so minus 1 over 2 squared, and then for k equals 3 we have minus 1 cubed, which is minus 1, with this I cubed, which is minus I times minus, yeah, it's just minus I, so that will give us plus I, with minus and minus will cancel, over 3 squared plus 1 over 4 squared. And at this point it seems that we are not going anywhere, but don't worry, let's just group the I terms and the non-I terms together. So grouping the I terms, we have minus I over 1 squared plus I over 3 squared and minus I over 5 squared if you want to continue, and so on. Plus then the non-I terms are minus 1 over 2 squared plus 1 over 4 squared minus 1 over 6 squared, and that goes on. So now let's take out a common factor of negative I. From here we have then 1 over 1 squared minus 1 over 3 squared plus 1 over 5 squared, and so on. And why don't we pull out a factor of minus 1 over 2 squared, because there are all even terms, so 2 will always be a factor in all of them. So we obtain 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared, and that goes on. Let's try to find a generalized form for this. We can express this as sum from n equals 0 to infinity of minus 1 to the n over 2n plus 1 squared minus this will be 1 over 4, and we have sum from n equals 1 to infinity of minus 1 the n plus 1 over n squared. So this by definition is Catalan's constant. So we have minus I times Catalan's constant, and we have minus 1 over 4 times, this is just the Dirichlet eta function of 2. Simplifying, we have minus I times Catalan's constant minus Dirichlet eta of 2 is famously pi squared over 12. So pi squared over 12 times 4 is pi squared over 48. And what was this? This was basically this series that we had to deal with. But an interesting observation here that this series that we had to deal with can be expressed as basically minus I to the k over k squared summed from k equal 1 to infinity, right? Using this, which just translates to the Dilogarithm of negative I. So not only did we solve this series, but also found a nice closed form for the Dilogarithm of negative I. So that's a really beautiful result that we obtained during this process. Anyways, let's just plug everything together now. Okay, so just plugging everything together in, we have 1 over 2i, and then this series just turned out to be minus I times Catalan's constant minus pi squared over 48. And this, as I said, is Riemann zeta. My zetas are always messed up, I'm sorry about that, of 2. So we have the i's cancelling out, so we have negative Catalan's constant over 2 and negative pi squared over 96i, and Riemann zeta of 2 is pi squared over 6. This series has a famous result. Then pi squared over 6, and this 2i will make it pi squared over 12i, but 1 over I is negative I, so we can still simplify this to minus Catalan's constant over 2 plus I times pi squared over 96 plus I times pi squared over 12. Again, we can take an LCM, so we have minus Catalan's constant over 2 plus I 9 pi squared over 96, which if you want to reduce is minus Catalan's constant over 2 plus I times 3 pi squared over 32. That's S, the sum that we were worried about. So let's plug this back into our original expression for I. Okay, so reverting back to our original first page, this entire S will just be minus Catalan's constant over 2 plus I times 3 pi squared over 32 minus I times 3 pi squared over 32 minus pi over 4 times natural log of 2. The best part, both of these will cancel out with dignity, and I is just minus Catalan's constant over 2 minus pi over 4 times natural log of 2. Isn't that a really nice result? I mean, the Catalan's constant is just coming out of nowhere. We expected this pi because again we had a trigonometric function we dealt with, even the natural log because we had a natural log of sine, so we expected the pi's and the natural logs, but the Catalan's constant surprises us again. Fair enough. Let's just conclude everything now. Okay, so in conclusion, we had an integral I, which was defined as integral from 0 to pi over 4 of natural log of sine theta d theta. We used the exponential definition of the sine due to Euler's formula. Then we simplified stuff. We used Taylor series after converting the natural log in a convenient form. And then we dealt with the series separately, giving us Catalan's constant and using Riemann zeta and Dirichlet etas, we simplified everything down. The imaginary components cancelled out, which is great because anyways we would have ignored them. And the answer just turns out to be minus Catalan's constant over 2 minus pi over 4 times natural log of 2, which has an approximate value of negative 1.002379, if you just wanted to know. And that's if we look at integral from 0 to pi over 2 of natural log of sine theta d theta, the original one, we ended up with minus pi over 2 times natural log of 2. So it's almost like this pi and natural log divided by a multiple of 2 is almost like an expected behavior of an integrand of this form, natural log of some trigonometric function, in this case the sine. But the Catalan's constant was something that was pretty unexpected. That's why this integral is pretty strange, and it's pretty important to my playlist of trig integrals. And if you want to just look at I naught, which is defined as integral from pi over 4 to pi over 2 of natural log of sine theta d theta, you can just use the linearity of the integrals. So integral from 0 to pi over 2 of natural log of sine theta d theta minus integral from 0 to pi over 4 of natural log of sine theta d theta. This we know to be minus pi over 2 times natural log of 2, and this, all of the minuses will cancel out, will just be Catalan's constant over 2 plus pi over 4 times natural log of 2, which if you want to take an LCM will be g over 2 minus pi over 4 times natural log of 2. So again, this is a very nice integral if you want to look at. We solved it quickly using these two values. And that's it for this video. Hopefully you learned a lot. So hey, please like, share and subscribe to my channel. Recommend me to your friends. I really want more subscribers. And you can check out my Instagram, gamma_digamma. In the meantime, stay home, stay safe. And don't forget to remember this result for the next video I'm going to make. It's going to rely heavily on the processes that we've used for this integral. So remember that and stay safe. Peace out.